And I'm ready to go. So I had a few questions emailed. I can address some of these questions in a general sense. And if people have, specific ones, if anyone has anything special they'd like me to start out with, I can do that one too. I kind of know what the trouble areas are. The midterm is put together now. And if you want just a general breakdown, it's going to be very similar to the last one, except we've gone from 22 multiple choice in the last one to 20. So it's slightly shorter, 10% shorter, I guess. And covering 5 and 6. Sorry, 6 and 7, chapter 6 and 7. We have long answer as well. It's about the same as the last one. Of course, it's going to focus heavily on 6 and 7, which has a lot to do with reactions and mechanisms, identifying what the correct mechanism is under a given set of conditions, and drawing the correct product given starting materials and conditions, and drawing the mechanism, all the steps, lone pairs, curly arrows, all that stuff. And so we can spend a good amount of time tonight, as long as you guys are willing to listen. We can look at examples and show you how to handle questions like that. I should mention too that you can't forget everything that we did before as well. In particular, like RS is something you still have to know how to assign. And all the sort of the cyclohexane chairs that might come into play again, as that did in chapter 7 when we looked at E2 reactions. So there's a lot of skills that we learned early in the course that while we're not explicitly testing, you still need to know how to do those. So do you want me to jump in and just do some reactions? I'm going to do that because that's what I want to do. There we go. Let's say, okay, great. Thanks, Elise, for the vote of confidence there. Let's say we have an example like this. Start with an alcohol, and we are going to react this under conditions of HCl. Now, these are a set of conditions that you would have seen in chapter 7, unit 7, and when you look at one of these, if you get a question and it gives you this and it says either draw the mechanism or draw the product, the first thing you should look at is the starting material an alcohol or an alkyl halide? And in this case, it's an alcohol. So what do we know? It's an alcohol. We know we have an alkyl halide. Sorry, we have an alcohol. I'm already distracted here. And then what you should figure out is the alcohol primary, secondary, tertiary, or methyl? And in this case, the way you would do that is you look at the alpha carbon and you check to see how many beta carbons there are. A carbon attached to an alpha is a beta. So in this case, we have 2 betas. So this is going to be a secondary alcohol. So if you look at the conditions and you look at what kind of alcohol it is, that's how you can figure out what the reaction mechanism is going to be. So the choices are methyl, primary, secondary, tertiary. And in terms of conditions, there's only 2 sets of conditions we would give you. It's going to be H2SO4 or H3PO4. It's the first set. Second set would be HX, like HCl, HBr, HI, one of those 3. And in those cases, if it is secondary or tertiary, it's going to do a mechanism which involves a carbocation, which is SN1 or E1. Phosphoric acid and sulfuric acid are both E1, and HX would be SN1. Because the anion from HX is Cl minus, Br minus, they're good nucleophiles, so they do SN1. Methyl and primary can't do that because methyl and primary can't form carbocations. So in these cases, you would have E2 SN2, SN2, and methyls cannot do elimination. So nothing's going to happen with the methyl. All right, so if you go back to the original ones that we have here, you can see we have a secondary alcohol and we're reacting it with HCl. That's this box that we're looking at right here. So it's secondary, so it can make a carbocation. So it's going to be something 1. And the chloride that's in the starting material here is a good nucleophile once the H plus leaves, so it's going to be substitution. So let's say the question said, draw the complete mechanism and show the major product. Well, we can do that. I'm going to just slide down a little. We're going to take our alcohol, we're going to react it with HCl, and I'm going to draw in, when we do mechanisms, it's good to draw in all the lone pairs. In fact, I think we often ask you to draw in all the lone pairs. So we have our alcohol, we have our HCl, and whenever you have a strong acid, the first step of the mechanism is always going to be proton transfer from the strong acid to whatever the molecule is. So in this case, we have an alcohol. It's going to do a proton transfer, which has curly arrows that look like this. So what that does, it makes the oxygen on the OH have an additional bond to hydrogen. It has 1 lone pair left, and the chlorine has the original 3 lone pairs. Now it has an extra one that came from the bond, the HCl bond that just broke. So those electrons go there. Formal charges, we're going to have a positive on the oxygen and a minus on the chlorine. And those are just following the rules of formal charges that we did back in Unit 1. Now for SN1, the next step of this reaction is to lose the leaving group. OH minus is an awful leaving group, but when you protonate it with a strong acid to make an oxonium ion, that turns the OH into a great leaving group because it can leave as a molecule of water. So what happens then is that goes. Notice the curly arrow starts at the bond, the CO bond, and it points to the location the electrons go. So they're going to end up on the oxygen atom. Great. So now we have our carbocation here. See, there was a hydrogen back there that we haven't been drawing in. That hydrogen is still there. Our water molecule is floating away up here somewhere. It's got 2 lone pairs now because it has the original lone pair plus the lone pair from the CO bond. And we have, come back. Plus we have the Cl minus. Now, next step is we have a nucleophile and we have a carbocation. Carbocations aren't very stable. Nucleophiles love to react with carbocations. And so it can come in, starts at a lone pair on the chlorine, goes to the carbon with the positive charge. So that means it's going to form a carbon-chlorine bond. So the chlorine only has 3 lone pairs after that because it had 4, but it used one of them to make that new bond, so it has 3 left. And that's it. That is a full SN1 mechanism for an alcohol. Now this one, I'd say it's about as routine and straightforward as we can get because there's nothing we had to worry about. We didn't have to worry about stereochemistry. We didn't have to worry about anticoplanar, which you do for E2. We didn't have to worry about rearrangements. Yeah, those are the things we have to think about in certain situations. So a lot of the email questions that I got were around rearrangements and how to spot them, how to handle them, how to know what to draw. And so I'm going to do an example with a rearrangement next. So let's do a new one. Let's do something very similar. We're going to put two methyl groups onto our carbon that you see right there. Can put in some lone pairs, and in this case, let's use H2SO4. So this is again a secondary alcohol. Again, we have a strong acid, but in this case it's sulfuric, and sulfuric will do an E1 under these conditions. And if you go back to our little chart up here, we're going to be in this block, secondary with H2SO4. So it's E1 is going to be the main mechanism here. So to draw this out, I'm going to start again down here. I'm going to draw out the Lewis structure for sulfuric acid. Get all my lone pairs here. Sulfuric acid is a strong acid, and strong acids, first step, proton transfer. So we're going to transfer a proton here to the oxygen, which will look the same as it did in the previous step, previous reaction. And that gives plus the anion. And generally speaking, we don't care too much about the inorganic products in these examples. I mean, not that they're not important, they are important and sometimes very important. Well, in the last step, the inorganic product of the first step was chloride, which we had to bring back in as a nucleophile. So yeah, sometimes they're very important. But we get this far, we make our oxonium ion. Oxonium ions will lose water quickly to make a carbocation if it can make a stable carbocation. This is E1, so the next step is making the carbocation. Carbocation looks like this. And again, there is a hydrogen here, there's hydrogens here, and there's methyls on the left-hand side. So this is an example, like if you're looking for rearrangements, this is the point where you stop and think, can there be a rearrangement in this case? And that's because this carbocation is a secondary carbocation. If it's a secondary carbocation, that's where we have to watch out and be careful for possible rearrangements. If it's tertiary, you don't have to worry about it. If it's primary, you already screwed up. Don't draw primary carbocations. If it was primary, it probably was going to be an E2 or an SN2. Okay, but in this case, we're secondary. And so what we do, if you have a secondary carbocation and you want to look for possible rearrangements, is you look for the alpha, look for the beta, look for the beta. And the things that we can switch over are alkyl groups or hydrogens. And you can explore all possibilities if you like. If you look on the right-hand side, let's say we move one of our hydrogens that's on the right side. The way that would look is the curly arrow starts at the CH bond and points to the carbocation. So that means the pair of electrons in that CH bond move one spot over to the carbon, and the hydrogen goes with it. So that would look like this. So the original hydrogen is here. Here's what I'm going to do. I'm going to erase that hydrogen and draw it back in green. Just so you can see which one moved. One of the blue hydrogens moved, and the green one stays put where it was. And where the electrons left from, that's where the charge goes. So just look at this very carefully. When you do a rearrangement like this, when you do a hydride shift or a methyl shift or an alkyl shift, you only need one arrow. One arrow is all you ever have to draw. You don't need two. You don't have to do what a common error I see is people will do something like this to show the charge moving over. That's incorrect because you don't use arrows to show movement of atoms or positive charges, strictly for negative charges. So let's get rid of that. Now, look what we did. We switched one of those beta hydrogens over, but what that did is just made a different secondary carbocation, right? This one is still secondary. It has 1, 2 betas, 1 alpha. A secondary to a secondary is not a productive rearrangement, so this is not one that we would draw. This is not something that we should be looking for. So what we do instead is look at the other side, look at the other beta hydrogen, and look to see if one of those things can move. So in this case, we have 2 methyls, 2 CH3s. Let's try to move one of those. I'm going to get rid of my arrow here from before, put our beta back, and that would look like this, pointing to the carbon, starting at the carbon-carbon bond. So what that would look like is we have our green hydrogen still there. We now have a new methyl that shifted over. We have 1 methyl still at the original place, and the positive charge moves to where the methyl came from. So the positive charge is here. What kind of carbocation is this? You can use the chat if you want. Tertiary, great. So this is a great rearrangement because it converted a secondary carbocation into a tertiary carbocation, and this will be fast, and our major product will come from this carbocation. This reaction was an E1, so we got to do elimination here. Notice that in that step right there, we also lost a molecule of water. We did the dehydration. So we want to bring that water molecule back because we need a base. And the conjugate base of a strong acid is not a good base. But water is all right. So we can take water and we can remove a beta hydrogen. Remember, this is alpha, beta, beta. Can remove that beta hydrogen just like that. And that will give as our product methyl here, double bond. Now notice there are 2 other beta carbons with hydrogens, right? There's hydrogens here, and that CH3 up there is all hydrogens. So we took the blue, or we took the green one there to make that product. If instead we picked one up off the methyl, you could imagine making that product instead. Or if you took it off of one of those positions, the bottom left positions, you could imagine making this alkene. So this reaction might be a little sloppy. You might get a mixture of products here. But what we can do is we can use the Zaitsev rule to figure out which of these is going to be the major product. So we look at the 3 alkenes, and these are all isomers of each other. What we would do is check to see how substituted these are. And I mean, if you look at the far right one, if you look at the carbon-carbon double bond, which I went over in red, we have 1, 2, 3 carbons attached. So this would be tri substituted. This one has 2 carbons attached. This one's di. And it's not just any old di, it's CHEM di. They're geminally di-substituted. And how about this one? This alkene has 1, 2, 3, 4, which makes it tetra. Tetra. So in terms of alkene stability, the ordering goes tetra is most stable, tri, and then trans di. Cis di is about the same as gem di is better than mono. Question, would tetra and gem be the biggest factor to decide which is better? Absolutely, yeah. So that's Zaitsev's rule. Whichever product is most substituted will be the one formed in greatest amount. So this one we would say is major. And what that actually means, maybe that's 80% and then all the other ones together add up 20%. I mean, we don't know what those numbers are and nobody can predict those easily. We just know which one would be produced in the greatest amount. Cool. Can you remind us why Zaitsev was decided for this reaction? Yes. So every elimination reaction, Zaitsev's rule will apply, except in one case. The one case where Zaitsev's rule doesn't apply is when it's an E2 and you're using a bulky base. This would be something like, in fact, we almost always use the same bulky base. It's like this, or, okay. Basically, what this is equivalent to is O minus. So you have a bulky base, a bulky alkoxide. Instead, these have a hard time doing the Zaitsev elimination. So instead, these do Hofmann, which is the opposite. It gives you the least stable alkene, yep. It gives you the least stable one because, so like an example would be if you have, let's say you have a carbocation that looks like this. All right, this is our alpha. We have a beta, beta, beta. Let's put our hydrogens in green. And, these methyls here, they're kind of big, right? That hydrogen right there is kind of tucked away. It's kind of surrounded by these big methyl groups. So if you have a base that's also big, it has a difficult time accessing hydrogens that are kind of buried in like that. So instead, what it'll do is it'll go for these ones that are kind of hanging out in the breeze there, like they're very exposed, very easy to grab. So a bulky base will give you this product as major, which is the Hofmann alkene, the less stable possibility, versus if you had a small base, like, I don't know, like this. If this was a primary alkoxide, this one up here is a tertiary alkoxide, tertiary is bulky, then you'll get Zaitsev. So if you're doing using sulfuric acid, like we are, if you're doing elimination on an alcohol, it's always Zaitsev because our base is like a little tiny water molecule. So yeah, anytime you're doing elimination on an alcohol, always Zaitsev. Whenever you're doing elimination on an alkyl halide, still always Zaitsev unless you have a big bulky base, and then it's Hofmann. Cool. Perfect. Let's try. Would you like one that's maybe a more complicated version? I'll give you the hardest possible rearrangement question. So yeah, I see a question there. Are there ring expansion questions on the midterm? I don't think there are. Yeah, no ring expansion ones. I'll do a ring expansion one to show you. I can't promise there'll never be one in the future, but I wouldn't rank it up there as your first concern. But the ring expansion ones, they look difficult, but they're really not that different than the ones we've seen so far. So let's say we're going to do this. We're going to react it with HBr. According to our trusty old chart, secondary alcohol with HX should be SN1. First step, proton transfer. Whenever you have a strong acid, that'll always be the first thing that happens. That makes an oxonium ion, just like the last couple of examples. And then it will lose water. That wasn't a very good arrow. Maybe more careful with it. There we go. Much better. Starts at the CO bond, points to the oxygen where the electrons go. These kind of compounds, by the way, with those sort of two rings joined at one spot, these are called spiro compounds. Okay, so that goes, water is up here somewhere, came off as a leaving group. And we still have bromide around too, don't forget. But we have a cation. This is secondary. The process I went through last time to look for rearrangements, these get faster as you do more examples. You might see right away that it's not going to be productive to do a rearrangement with the CH2 on the left, because that'll just move the positive charge to that position, which doesn't get you any further ahead. But what this can do is a ring expansion. And if you ever have one with a ring expansion, the first thing I suggest you always do is label all your carbons to begin with. Because the biggest mistake people make here is losing carbons or adding carbons in from nowhere. So 1, 2, 3, 4, 5, 6, 7, 8. So we got to be very sure we have 8 left in our original. So what would happen with a ring expansion is, if you look at it like this for a second. Let's say I erase those to leave you with this. This would be a straightforward. This is like the one we did in the previous one. This we'd look at it and we'd say, okay, methyl shift, no problem. That would give us this, right? Well, what we're going to do is just join these. Join them like that. That becomes 7, 8. If we label the carbons back here, 1, 2, 3, 4, 5, and 6 was the methyl here, 8 was the methyl there, and the only one we're missing was 7. 7 joins 6 and 8. There we go. That might not have seemed that simple the way I did it. I'm going to go through that process again. I'm going to delete all this. We have our original cation. The 1, 2, 3, 4, 5 ring doesn't change. It's the 1,8 bond that breaks. It's the only one that breaks. So let's redraw 1, 2, 3, 4, 5. Okay. We're breaking 1,8, but we're not breaking 1,6. So 1,6 is still intact. And what we're doing is we're breaking 1,8 and making a 2,8 bond. So 2, I wanted that color, 2 should be bonded to 8. Now 6, 7, 8, we didn't break any of those bonds, so 6, 7 and 7, 8 are still there. And what happens is if you move the 1,8 bond to carbon 2, the positive charge will go down to carbon 1. Then we can finish this off. This was a substitution, so we have bromide attacking our carbocation. Big long curly arrow from there. And we get this nice looking thing. So that's a ring expansion. I know you guys don't like ring expansions, so I don't want to spend too much time on them right now because there's lots of other good stuff to talk about. All the examples we've done so far are alcohol reactions. We have alkyl halides as well. Alkyl halides are actually more complicated than the alcohols because, you know, all the reactivity of alcohols can be summarized in this one table that you see right here. Alkyl halides is a bit more complicated because there's a bigger variety of what can happen, and there's a bigger variety of conditions that we can subject it to. Would you like to have a breakdown of what happens with alkyl halides? Nobody objected. So yes, let's do it. Okay, just like alcohols, alkyl halides can be methyl. They can be primary, they can be secondary, or they can be tertiary. Make a nice table here. Okay. So the conditions that we can have, I wonder if I cut this whole thing and move it over here. Give me some more space. We're going to have conditions that look like 1, 2, 3, 4. So these are the conditions that are possible. So by the way, when I say methyl, what I mean is something like CH3Br would be an example of a methyl bromide. Primary would be like ethyl bromide. Secondary would be something like Cl. Tertiary, something like that. Possible leaving groups are chlorine, bromine, and iodine. Fluorine is not a leaving group, nor is hydroxide, unless you protonate it first. Okay, so we have first conditions are bulky base. Something like that. They're almost always together with the conjugate acid, which is the alcohol, as the solvent, Protic solvent. And when I say bulky base, what I really mean here is bulky alkoxide, which are strong bases. They're really good at promoting E2 reactions. Next conditions you can have is a small alkoxide, like this. It could be ONA, it could be OK, it could be OLI, it could be methyl, it could be ethyl, it could be propyl, doesn't matter, as long as it's primary. You can have strong nucleophile. Strong nucleophile is typically something that's negatively charged. Examples of strong nucleophiles would be azide, SH minus, CN minus, any halide like chloride, bromide, iodide. Anything else that we used as strong nucleophiles? Probably something else. Basically, if it's got a negative charge and if it's not an alkoxide and it's got a negative charge, it will be under the strong nucleophile category. These are typically put, when you draw the conditions for these, they typically also have a counter ion. So you might see something like NaN3 or NaSH or KCN or something like that, NaCl. So those are all strong nucleophiles. And the last thing is you have no strong alkoxide, you have no strong nucleophile. All you have is polar protic solvent, and that's it. This would be something like water is a polar protic solvent, or ethanol is a polar protic solvent, or maybe acetic acid is a polar protic solvent. This covers every possible set of conditions that you will be given on this midterm or on the exam or in the notes or in the book or sapling or anything else. So bulky alkoxides really love to do E2. They're terrible nucleophiles because they're bulky. They only like to do elimination, and so they like to do E2. They do E2 right across the board except for the methyl bromide, because you can't do elimination at all on a methyl compound. Because to do elimination, you need an alpha carbon and a beta carbon at a bare minimum. Methyl bromides have an alpha, but they don't have a beta. You can't make an alkene with one carbon. So this cannot possibly do elimination. In fact, the only thing methyl bromides can do at all is SN2. They can't do any sort of elimination, and they can also not do SN1 because they cannot make a carbocation. So this whole line here going down is going to be SN2, 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 SN2. That's the only option available to methyl compounds. So other than that one, bulky alkoxides will do all E2. Small alkoxides also like to do E2, except in the case of primary. Primaries are really fast at SN2. So primaries typically will give a major product here of SN2. It'll probably give some E2 as well, but typically SN2 is major. SN2 is really fast for primary alkyl halides. Now, that's kind of it for the alkoxide group. For the strong nucleophiles love doing SN2s. So it'll do SN2 with the methyl, as we already said. It'll do SN2 as well with the primary. It'll also do SN2 with a secondary, but it's starting to get a little cluttered, right? The back end of this molecule that the nucleophile has to attack is starting to get kind of increasingly blocked up. So tertiary alkyl halides cannot do SN2s. It's just too bulky on the backside, so that's not an option. It's not going to do elimination because we don't have a strong base. So what these are going to do instead is SN1 for lack of any other options. All right, the last ones we have are polar protic. Someone just asked for control and it lost my thing here. Now we're back. Polar protic and polar protic are not very strong really at anything. They're not, they don't have a negative charge. So they're not going to force the action. They're kind of not particularly reactive. But they're going to do an SN2 with a primary alkyl halide. And for the other two ones, you're going to get carbocations formed. Polar protic solvents are actually great for forming carbocations. And these ones can either do SN1 or it can do E1. And often you get a mix. But the way we're delineating these, if I can cut them in half like this, E1 has heat. So raising the temperature, doing these at a higher temperature, will favor elimination over substitution for the reason that elimination reactions have a higher positive delta S. They increase the entropy of the system more than a substitution. And that's because they make more particles than substitution. Substitution gives you the same number of particles you started with. E1 gives you additional particles. So it's an entropy reason. Higher temperatures favor reactions that have a higher positive delta S. So if you see conditions that have heat, then do E1. And if you don't, or if it says room temperature or cold or something like that, do SN1. So this is quite a bit more complicated. In fact, it gets a little more complicated further because these E2s in the top row with the bulky alkoxide, because it's bulky, These all are Hoffman, right? Those are the only cases we said Hoffman was an issue. All the other eliminations are Zaitsev. And down here as well. Great. Tristan, I see your mic off there. Do you have a question?
Yeah, did you write ethanol as both a small alkoxide and a polar protic solvent?
No, ethanol on its own is a polar protic solvent, and that's it.
Okay.
When you have an alkoxide, like here, you'll have ethanol there as the solvent, but you'll also have the alkoxide.
Oh, okay.
So down here, when you have a polar protic conditions, you have only the alcohol and nothing else.
Right.
Yeah. So whenever you have an alkoxide or a strong nucleophile, you need a solvent there as well. So for the nucleophile, strong nucleophile, typically if you want to make an SN2 reaction faster, the best solvents to use are polar aprotic solvents, like DMSO, DMF, acetone, acetylnitrile, etc. So how about we do some examples? Because this is a whole lot of information on this one page. And if you're on the Instagram account, there's a post that's still up there with all this information on there. But let's apply some of this and see some examples as you might see them on the midterm. So if I gave you a molecule like this, here's what we do. We start out, we look at our alkyl halide. We would check to see if the alkyl halide is primary, secondary, tertiary, or methyl. So to do that, look at the alpha. We count how many betas there are. There's 2 betas, so this is secondary. 2 prime. And we then look at the conditions. And whenever you see something with sodium or potassium or lithium, we have to separate these. We dissociate them so that we have Na plus on one side, SH minus on the other. So we look at the negative charge side. Sodium plus we would call a spectator ion. It doesn't do anything. It just kind of watches, flips around. The other one, the SH minus, is not an alkoxide. So we would call that a strong nucleophile. So we can go up and look at our table and look up a secondary alkyl halide and strong nucleophile, and they intersect here where it's SN2. So SN2 is what we want to draw. SN2, if we want to draw this mechanism out, has a mechanism with one step when you have alkyl halides. It's the nucleophile attacks the alpha carbon, the leaving group leaves, there's an inversion of configuration, and the reaction's complete. So if you look at this bromine, there's a chiral center here, and the stereochemistry of this chiral center is S, the way I've drawn it. So we're going to use this as our nucleophile. It's going to come in and attack, and the CBr bond breaks, and the electrons go to the bromine. And all in one step, you have the SH come in, and bromide is kicked out. Notice the SH that I've drawn is using a hashed bond, not a wedged bond, and that's because we've inverted the configuration. Inversion always happens with SN2s. And so our product is going to be our stereochemistry. Now, S doesn't always become R, and R doesn't always become S when you invert it. It depends on the relative priorities of what you're losing and what you're adding on. There's cases where you may, it might go S to S, but there's always going to still be inversion, right? Because S and R depends on what the groups are and what the priorities of those groups are. So there we go. That would be an example of an SN2 reaction. And that's what I'd like you to draw. You need to draw, in this case, there's only one step. You draw the step, and curly arrows, all my lone pairs are there, all the products. Everything that I would like to see is what's drawn here already. Cool. Do you have to look for inversion only in SN2 or whenever there's a chiral center? So I'm going to answer this with an example. Okay. Here's the example I want to give. It's going to look like this. Here we go. Alkyl halide, sodium iodide, and acetone. So sodium iodide is, we should think of this in our minds as being like Na plus, I minus. So it's I minus is the reactive part here. And we have acetone, which is a polar aprotic solvent. It's great for SN2s. However, our starting alkyl halide here is tertiary, because we have our alpha, we have our beta, and our beta. So because it's tertiary, it cannot do an SN2. And if you look at our chart, strong nucleophile and tertiary is SN1. Okay, so SN1 is what we need to draw here. And if you look at the stereochemistry of our starting molecule, this will be an R stereocenter. So that's something you still need to be able to do, is look at a stereocenter like that. It might take you longer, but assign priority to the different groups, orient it so the low priority group is pointing back, and then identify it as R or S. This one's R. This one is SN1, and SN1 doesn't involve inversion. This one involves loss of stereochemistry, is what we would say. So the first step of an SN1 is formation of the cation. So the chloride just pops off, and you're left with plus. And then Cl minus. I want you to pay close attention to the way I've drawn this. I've drawn it with all just normal straight bonds. It would be a mistake to draw this like this. That's not very clear maybe. If you kept the wedge bond from before, that's actually incorrect, because it implies that the geometry of that carbon is still like, I don't know, trigonal pyramidal or something like that. When you have a carbocation, it's flat, planar. In fact, trigonal planar would be the shape. It's sp2 hybridized. So we want to draw it flat. We want to draw it like you would draw any trigonal planar molecule, no hashed or wedged bonds on a carbocation. That's a little aside. So we have a carbocation here. Is that standard for all carbocations? Yes. Yes, no dashed or wedged bonds on carbocations. Now this chloride can come in and attack that carbocation. Because it's flat, think of it kind of like a sheet of paper. It can attack from the bottom or it can attack from the top. And whether it attacks from the top or the bottom determines which product you get. Some questions we might say, and by might, we'll say something like, if there's more than one major product, show both major products in the mechanism. Okay, so I'm going to do that in this case because there's two major products here. It can attack on the top or the bottom. If it attacks on the top, it will look like this. We can call this one top. You can see the chlorine kind of came down from the top. Why would the Cl be attacking if that's where it started from? You are correct. So let's not use Cl. Let's use iodide. There. Let's get rid of Cl. We don't want to see him anymore. Iodide is the incoming nucleophile. It can come from the top or the bottom. And let's get rid of chlorine there and put in I. So that's the top. Or it could come in from the bottom instead. So in the top example, we have S, and in the other example, we have R. In this case, I would expect 50-50 because that cation is a flat surface. There's no preference for it to come from the top or the bottom. Which way it attacks from will just be a total accident based on where the iodide happens to be when it comes in contact with that cation. So that means there's no preference. You have a 50-50 mix. These two molecules are enantiomers. So what do we call a 50-50 mix of a chiral molecule plus its enantiomer? Yes, racemic. Racemic, good. This is a racemic mixture we would get. So this is an example where you are doing a substitution. What was the original question? Do you have to look for inversion only in SN2 or whenever there's a chiral center? So here there's a chiral center. It's not inversion, but you do have to take care of the chiral center. So it's true, inversion, strict inversion, 100% inversion happens only with SN2. With SN1, we kind of get a racemic mixture. We get a mix of the two. And so you have to pay attention whenever you have a chiral center, what you're going to get as a product. Cool. Anything anyone else would like to see in particular? Or do you want me to just keep going on with random examples? So just clarifying, if you ask us to draw an SN2 mechanism like the first one, there would only be two curved arrows. Yes, that's correct, Sydney. Only two arrows. With SN1, there's also only two arrows, but they're in two separate steps. Elise is asking to do something with chairs. I can, yeah. And Sam, I see your hand up there too.
Yeah, can you do an example of where you have like two products, but they're not racemic?
Sure. So,
if that's like even a question we'll get.
What would be an example of that? Elimination, you can have that happen. But substitution, unless it was a weird example. I mean, we're sticking pretty straightforward, I think, with the examples we're giving you on the midterm.
Okay, if it's not something we'll see, then don't bother.
Yeah. If you see a question that says, if there's more than one major product, draw them all, this is referring to this SN1 case where there's R and S possible. There was one like that in the chapter 6-7 practice if you watch Terry's solutions. Elise, if you can if you have a screenshot or something to show me, and you can put it right in the chat too. I can address that. I'm not quite sure what you mean. But we can do something with chairs if you like. Oh, I see another hand up. Oh, for Sam's question. Yeah. We have another hand up there as well. I can answer that question too if you like, before we jump in.
Yeah, I'm just wondering for like rearrangement questions, right? Mm-hmm. So if we have a situation where we can choose between moving a methyl group or hydrogen, what do we choose, assuming both of them will lead to a tertiary carbocation?
Yeah, this is a case that we almost never ask. The answer is methyls. And it may seem counterintuitive because hydrogens are smaller. Hydrogens should move faster, you would think, but methyls actually do move faster. So, you know, I'll give you an example. If you had a cation that looks like this, okay, so there's a hydrogen here. You could do a hydrogen shift from the left, or you could do a methyl shift from the right and make this. This one's actually better, but I don't think you have to worry about this situation coming up. We're not going to ask you that one. The reason why that one's better, it has to do with the mechanism for how the shift goes. So that particular shift, if you have the cation here, right, we draw it like this, but it goes through a transition state where it's sort of like half transferred over, like you're breaking one C bond and you're forming the other one. You have a positive charge in that ring. That methyl group does a better job of stabilizing that charge than a hydrogen does. So it has a lower energy transition state, so it's faster. But that's a very good question. It's sort of a niche kind of edge case example that we try to carefully avoid because it's, to me, I don't know, that's sort of a level of detail that we don't really need to get into. But yeah, thank you. That was a good question. Let's look at an elimination on a cyclohexane ring as requested by Elise. Correct, on a chair. I'll do an example of a question that I put on, like every couple of years, I'll put this on the final exam and almost nobody gets it right. And that's why I keep putting it on. Because you can see all our old exams, right? So you'd think people would start getting it right more frequently, but hasn't been the case yet. Give you this molecule and give you a nice small alkoxide like ethoxide, sodium ethoxide. Solvent here is ethanol, but don't confuse this for polar protic solvent conditions. It's not. This is alkoxide conditions because the negative charge thing there is going to be the one driving the action. We want elimination, so normally we'd put a little triangle there for heat. I told my section what the triangle means, why we use triangles. It's the ancient alchemical symbol for fire. They used to believe there was only 4 elements, fire, air, water, and earth, none of which are actually elements. But the alchemical symbol for fire was a triangle, and we keep that. And so the question says this reaction only gives a single alkene as a product. Draw the structure of the alkene. And people look at this and they say, well, okay, look, this is going to be E2. And to do E2, you need to remove a beta hydrogen. And when you're on a cyclohexane ring, we have this requirement with E2s that the hydrogen and the leaving group be anti-coplanar. And that's only achieved when the leaving group is axial and the beta hydrogen is also axial. So in this case, what you could do is convert this to the cyclohexane chair. Looks like this. And the way I like to think about this is if you see a wedged bond, consider the group up. And if you see a hashed bond, consider it down. And we're going to look at these carbons. Let's say 1, 2, 3. We're going to go 1, 2, 3. So carbon 2, the one with the bromine, has an up and a down. Carbon 3 is an up and a down. Carbon 1 is an up and a down. So the way I've drawn this, the 3 methyls are all in the up positions. CH3, CH3, CH3. The down positions are the hydrogens. Now, the way this is, you can see the hydrogens on the ring, the beta hydrogens on the ring on carbons 1 and 3 are axial, which is great. That's where they have to be to do an elimination reaction. But the bromine is not. The bromine is equatorial and is not in a position where it can do an elimination. So let's try a ring flip. A ring flip would look like this. That's really bad. I'm embarrassed by my ring. It's really bad too. Don't worry, I'll get it eventually. There we go. Okay, so carbons 1, 2, 3 are here. These are the positions. The up positions are still methyls on all 3 cases. And let's put that methyl here. The down positions on 1 and 3 are the hydrogens. And the Br is down here. So in this ring flip form, you can see the bromine is axial, which is great. We need the leaving group axial to do an elimination. But the beta hydrogens on carbons 1 and 3 are equatorial, so we can't do that. So we can't do elimination in either form using the beta hydrogens on carbons 1 and 3 because the bromine doesn't line up. So how do we get our one product? And this is the tricky part. It's not really that tricky if you think about it. You have an alpha, we have a beta, and we have a beta, but we have one other beta up here too, don't we? We didn't think about that beta yet. Well, that beta is no problem. It's not on the ring. It can rotate freely, right? That's a CC bond that can rotate around no problem. It's easy for one of those hydrogens to be anti to the bromine leaving group. So what we can do is just use our alkoxide to do this. And the product that you get this. Or if you draw it out, so that one's a little bit tricky, I guess. But we don't have anything that tricky on this midterm. Too easy on you guys. Do you want a more straightforward version of a chair one? Maybe, let's say we just do this one. Great. We'll do bromine. We'll put a methyl there. And we will do, let's use a bulky alkoxide. Alkoxides always come in the alcohol they were made from. But you can kind of disregard the alcohol part here. It's the alkoxide that's going to be doing the action. This one is a secondary alkyl halide. It has 2 betas. A secondary alkyl halide with a bulky alkoxide, if we will go back up to our table, is E2. E2 is the one that does E2 is the one that requires the anticoplanar arrangement. So because this is on a cyclohexane ring and because it is E2, let's draw that thing out as the chair. Remember back in Unit 3 when we drew these out as chairs, and I think I said to my class at least that this is important and it'll come back later? Well, here it is. Okay, so let's pick carbons, I don't know, 1 and 2 and B1 and 2. And carbon 1 has positions up and down, 2 up and down. These are really hard to get right if you don't know how to draw the positions, the geometry correctly on these. Okay, so carbon 2, we would say the bromine is up and there's a hydrogen that's down. On carbon 1, we would say there is a methyl that's down and a hydrogen that's up. Now, in this conformation, the bromine is equatorial and cannot react. No E2 for this conformation because we need the bromine to be axial. Because if the bromine's axial and the beta hydrogen's axial, then we can get elimination. So we're going to do a ring flip. These are in equilibrium with each other. Carbon 1 is down here, carbon 2. Carbon 1, the methyl is down. The hydrogen is still up. Here, the hydrogen is down and the bromine is up. So this conformation is going to be the reactive one because the bromine is axial, if it can react at all. Now, under this conformation, it's a secondary alkyl halide, alpha, beta, beta. Just like up here, we have 2 betas. We were considering carbon 1, but carbon 3 is something else we have to look at. Carbon 3 has bonds here and here. So we can't actually do an elimination with the hydrogen on carbon 1 because the beta hydrogen has to be axial and the leaving group has to be axial. The only orientation where that's the case is this hydrogen and this bromine. Those ones are anti to each other, one straight up, one straight down. So we can do an elimination there. We're going to bring our bulky alkoxide in that we have from our conditions up here. We're going to get rid of the K plus and just have O minus. We're going to grab our beta hydrogen, kick that out, and that goes to the bromine. So this, if we want, we can leave it on the chair. This makes a double bond here. And the CH3 is still where we left it. We didn't react it there. Maybe an easier way to tell if you can do an elimination between a leaving group and a hydrogen on a ring. If you have a ring, the leaving group and the beta hydrogen have to be anti or have to be trans to each other. If trans, E2 is good. If they're cis, no reaction. Because if they're cis in this form of the structure, when you put them in a chair, you're not going to be able to arrange them so they're both axial. You can't make them anti to each other. Only the ones that are trans, like these two, will react. And if you recognize that, sometimes you can do these questions. Yeah, can I draw that one off the chair too? Like this, literally this one right here. So yeah, I can. Yeah, let's no. Which one are you talking about? The chair one. This one? Why don't you pop your mic on, Elise? Just ask me.
I was just wondering if you could draw the final chair as not a chair.
Oh, this guy up here. Yeah, for sure. What did it look like at the beginning? I'll draw it in the same orientation as before. That's really ugly looking. Tristan.
So, in a testing scenario, if we're able to recognize something like this, should we still draw it in the chair conformation, or can we draw it in the planar situation that we've got it right now?
If we explicitly ask you to draw it in the chair conformation, then do it. But if we don't ask it, if we just say draw the mechanism, you don't have to. So an example, if I do this exact same question here, like let's do it again. I don't know if I just copied that or not. I hope so. Yeah, I don't know how to copy it. I'm going back to my old way. So if I just say draw the mechanism, let's use iodine. We never use that one very much. And if you recognize that you can't, the hydrogen that's here, if you recognize that that beta hydrogen is cis with the iodine and you can't do elimination, but you can do that one, then you can just draw it like this. Sure you grab the right one. You grab the trans one. That's fine. You can do it all at one step. But if we do say, like, draw the chair conformation, blah, 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 if we want to see the whole thing, you do have to be able to do that. We ask you these in different ways. Like sometimes we'll ask you to draw the whole mechanism. Sometimes we'll just say, draw the major product. And if like you had to draw the major product one, you just need that. It's probably good practice, though, in every case to draw the full mechanism out, because sometimes you get products that you may not expect. For example, it sometimes is hard to see rearrangements if you don't draw out the mechanism step by step. Elise, if you ask us to draw the mechanism using chairs, should the answer be a chair or not? I'm flexible on that. You can draw it whichever way you like, as long as it's correct. Tristan again. Yep.
Can we look a little more into the shifts? I'm not as comfortable with that as I am Chris.
Yeah, another shift example. Let's use an alkyl halide this time. There we go. Ethanol heat. We have nothing negatively charged, no alkoxide, so it's not E2. No strong nucleophile. So this is a secondary. We have a protic solvent, that's polar protic solvent, and we have heat. These conditions all together are indicative of E1 mechanism. Go back up to our thing here. This would be polar protic solvent, bottom row, secondary. We're looking at this column. Okay, so we have E1. First step of E1 with an alkyl halide. Loss of the leaving group. Carbocation. Carbocation is secondary because the alkyl halide it was made from was secondary. Secondary carbocations are the ones we got to watch out for. So we have 2 beta carbons. And on the left-hand side, we have 2 hydrogens. Okay, if you have 2 hydrogens, we could hypothetically shift one of those hydrogens over. But if you did that, if you shifted one of these hydrogens over, and I think I remember I showed you sometimes these kind of loopy curly arrows are used if it's a rearrangement. You don't have to draw it that way, of course. Draw it if you like. Then that hydrogen, I'm going to put a green one up here. There was a green one here before. There was a green one in the original. There's a green one there still. That one shifted. Puts the cation there. That doesn't help. Tristan. Or is your hand just still up from before?
No, I've got another question. Is the loopy arrow just for hydrogens? If we were moving a methyl, could we use the loopy arrow?
Any rearrangement. It kind of just means the pair of electrons are coming and the atoms coming with it. I think that's only in a couple of textbooks. I don't think that's super widespread. So you could just draw it like an ordinary arrow if you like. But if you like the loopy arrow, I mean, if you find that that helps you keep track better, you're more than welcome to use it. But if you would rather draw it like that, you're fine to do it like that too. So this rearrangement that I drew gives you a different secondary carbocation, so that's no good. In fact, you might come to realize if you try every possibility out with every carbocation, if there's a CH2, you almost never want to move one of those hydrogens. It almost never helps. So in this case, on the other side, we have a methyl and we have a hydrogen, and we could move one of those. And maybe you can start, like after time, you can shift them in your head. You don't have to draw everything out, and you can tell what you're going to get. If you shifted the methyl like that, then what you're going to get is, let's draw back in our green hydrogen. Let's draw in the methyl that we just shifted. And that blue hydrogen is still left. And notice I did not draw a wedge bond here. It's a straight bond because this carbocation is planar. This just gives us another secondary. Secondary to secondary is no good. So last choice is we're going to move the hydrogen on that beta carbon. And I'm just going to adjust the curly arrow there a little bit. That, in addition to our green hydrogen, is our blue hydrogen that shifted. The methyl is still here, and that gives a positive charge. This is tertiary, so this is good. That's a good rearrangement, the hydride shift from that one. How do you know if you're shifting the alkyl or the hydrogen in this case? Because if you shift the alkyl, you get another secondary carbocation back, so that won't shift. But if you shift the hydride, then it makes this. Does that make sense, Lizzie? Yeah, you want to shift, you always want to go from secondary to tertiary. Perfect, great. So if I gave you a question almost identical to this, if I gave you a question that started like this, and those are both CH3s. Ethanol and heat, still E1, and we lose our iodide, pop in some lone pairs. That methyl is here. That's it. This is tertiary. That is not going to rearrange. So if it's tertiary at this point, you can just forget about rearrangements and move on. You only have rearrangements when you have a secondary carbocation. Now we got to finish this. We're not quite done. We need our alcohol, our solvent, to act as a base. And it needs to remove a beta hydrogen. This had 3 beta hydrogens, beta, beta, beta. It could make that product as major, Or it could have made or and why is this one the major product? Few people have hands up. Yeah. Zaitsev, yeah, more stable. It's tetra, good. Everyone's on board with this one. This one's tri, and this one's gem di. Good. Tetra is the most stable one. This is going to be a Zaitsev because it's not E2 with a bulky base. Cool. Ben, yes.
Hi, yeah. I was just curious. So if you gave us a question where the only like possible outcome from a shift would be a secondary carbocation,
Yep.
like is there any point in shifting it at all, or is that like
Nope.
would you just end up leaving it? Yeah, okay.
Just leave
Great.
it.
Thank
Yeah.
you.
No, an example would be if I gave you like this. Right, this would be SN1 because there's no heat. It's going to be a super slow reaction, but it could happen. So yeah, if you had a canister of this chemical and you spilled it into a lake and it's in water, this will happen eventually. Chloride will come off. You get a cation here, which is secondary, right? There's a hydrogen. You know, like you could hypothetically shift it like that. And then you'd have two hydrogens here and a plus charge there. This is also secondary. That will not happen with any appreciable rate. That's going to be not a good reaction because secondary to secondary doesn't get you any further ahead. So that's going to be super slow. Now, if you did this, you know, 1 in a million of your product molecules might arise from that. I'm not saying it's impossible or it could never possibly happen, but it's not an important pathway and not something you'd ever need to draw from me. Perfect. Good. So tertiary to tertiary is a no. Secondary to secondary is a no. Secondary to tertiary is the only one you need to worry about. Can we do those rotational type problems? Oh, the ones like that are on, they're E2 anti ones. And sometimes you see the Newman projections. Is that what you mean, Lizzie? You rotate it to be sister trans. Okay, great. Example would be if you have let's say you have molecule like this, okay? And so here we have a small alkoxide and we have heat. We have methanol as our solvent. And this is going to do an E2. And because it's small, we're going to do Zaitsev. So the way we would draw this is, you know, this is our alpha and this is our beta. The way I have this drawn, the beta hydrogen is anti to the chlorine, like the chlorine is going straight up. But if you were to redraw this molecule as a Newman projection, where this is the front carbon, you can redraw it where the front carbon has the chlorine up and the hydrogen down here and the CH3. And the back carbon would have the hydrogen down, ethyl that way, and the methyl up here. This is the correct conformation of the molecule above. And the way I drew this, the hydrogen and the chlorine are anti. And they need to be anti in order to do an elimination. So we can do the elimination either down here. Let me make that blue so I can be consistent. OCH3 negative charge will take the beta. That'll come up here. That'll come off. Or if you drew it up top here, it'd be like CH3O minus, remove the beta hydrogen. That comes off and that comes off. And so what you're going to get as our product here is, you can imagine forming the double bond, and the one in front, the one kind of coming towards us, is the ethyl, and the one going away from us is the methyl. So that's this group here and this group here. On the other side, we would draw the hydrogen going back and the methyl coming out here. So in this example, we would say, I mean, the way I'm kind of drawing this like you're looking at it on the edge. If you want to look at it from a different perspective, that's going to be like that. Right? And this has the bigger groups or the higher priority groups on both sides together, so this is going to be Z. So if I give you a harder example, like this. And this is only harder because the hydrogen is not anti to it. So if you were to draw this as a Newman projection, and let's say your eye was here, and you're going to look down the carbon-carbon bond. You're bald. You have an ear right around there somewhere. Or you could look at it from upside down the other way too. It doesn't make any difference. The way this would look from that vantage point is it would look to your perspective there that the bromine was up, and to your right would be the hydrogen, and to your left would be the methyl. And then looking over at the back carbon, which is over here, it would look like the one going down would be the propyl group, and going to your right would be the hydrogen, and going to your left would be the methyl group. Now, this orientation is in the wrong orientation to do elimination, because the beta hydrogen, which is this one, is not anti. So what you need to do is rotate this thing around. So it is anti. So if we leave the front carbon the same, and rotate it around so the hydrogen goes there, the methyl goes there, and the propyl goes there. Now we can do an elimination. Takes that one, that one, that one. And what you're left with is a carbon-carbon. I mean, this isn't really great because Newman projections aren't meant for alkenes. But if we kind of left it on the Newman projection, realizing that carbon-carbon bond's a double bond, there's a hydrogen and a methyl here, and then a methyl and a propyl over there. So if you looked at this from above, to see a normal perspective, it would look like carbon-carbon, methyl hydrogen, like that. So you might find that easier using the Newman projections. If you're not good with Newman projections, you may not find it easier using Newman projections. And then what you might want to do is just rotate the bond here using this form, making sure that the beta hydrogen and the bromine are anti, and then trying to draw the product straight that way, kind of like we did in this case over here. Does that make sense, Lizzie? Those ones can be tough. All right. What do I see? If it's towards you, do you just assume it's on the right? Depending on your vantage point, yes. I think it depends. At least I didn't even know this was an option. Sydney, can you draw the rotated version before you move any bonds? Alex, do we have to show lone pairs in drawing the full mechanisms? The answer is yes to Alex. Okay, so I think we have a couple of questions about these Newman projections again still. And Tristan, I see your hand up. I'll get to you in a sec. Maybe the easiest thing to do here maybe would try another example like this. See this one here, the one that's coming towards us is on the right only because that's the vantage I selected. So if you drew the same molecule, what did it look like? Hydrogen, but your vantage was that, then the one that's coming towards you, the hydrogen's on your left. So, you know, it could be left or it could be right. It depends on your vantage point. And you can select whatever vantage point you like. Doing these might be a lot easier if you have a model kit and you make the molecule too and you try it out. So Sydney says, can you draw the rotated version before you move any bonds? So you mean this question here? No. This one here, do it without Newman projections? Is that what you're asking?
Yes, like I guess I was just confused on how to look at it. Like the circled one that you have there, like I was asking if you could, like, it would just be on the next side is what I'm asking. Like, would it just be on the, when you rotate it, like how would it look before you move the H bonds is what I'm asking.
Okay, how would this look? Okay, you mean, how would the top molecule look if you rotated it like I did down here?
Yeah.
Okay, that one I can do. So the hydrogens are both in front. 1, 2, 3, 4, 5 carbons. So let's start us over again. 5 carbons. We have a bromine. We have hydrogen in front. And a carbon like this. Okay. The way I drew this, you might find it easier if you just turn the whole molecule on its side. So I'm not rotating anything here. I'm just flipping the molecule over. So I'm going to redraw it just like this. CH3 and does that make it simpler to visualize? These are the same thing. I didn't rotate anything. It's just the same molecule. It's like I took the piece of paper and just turned it. Perfect. Okay, so what I want to do is rotate this around because I need the bromine and the beta hydrogen, this is the beta, to be anti to each other. So when I rotate something, every time you rotate a bond, leave one side the same. So it's going to be easier, I think, to leave the left side the same. So we're going to leave the left just like we had it before. But now we need to rotate this around so the hydrogen's down here, because that's the position where the hydrogen's anti. And so to do that, the way you kind of have to rotate that is, why? Because to do an E2, and this is the whole thing we're trying to do here, we're trying to do an E2, the beta hydrogen and the leaving group have to be anti-coplanar. Not just on a ring, anytime you do this reaction. It always has to be anti-coplanar. That's why on the cyclohexane ring, they both have to be axial. When it's not on a ring, they have to line up. So to do that, if you imagine taking this, that carbon here, tying like a steering wheel to it, and we want to rotate it around that way. Okay, we want to rotate that side of the molecule around. So the hydrogen is pointing towards us, it continues coming towards us, and then goes straight down. So what will happen if you do that is this propyl group will kind of get turned in towards the back, like that. And the methyl that's already in the back will continue to turn around and point in front. Like that. So these two molecules are the same thing. All I've done is I left the left-hand side exactly the same. The right-hand side, I did a, 120-degree rotation to rotate the hydrogen so it's pointing straight down, so it's anti to the bromine. Then you can take your base. Now it's set up for E2. Now it can come in, grab a hydrogen, do our elimination. And that will give us a double bond. The hydrogen on the left is towards us, so it's still towards us. The methyl is back. And the other two groups, the methyl is towards us. Propyl is back. And we're looking at that kind of side-on view. That's the same thing as methyl hydrogen. Like that. So you can do it with Newman or you can do it without Newman, whichever you find easier to draw. Sam.
At that point, when you draw it, like when you redraw the CH3 and the hydrogen on the left side, does it matter if which one is like a dash and which one is a?
It does, yeah.
Wedge? Okay.
So just whatever you have here, draw them the same way there.
Okay.
So whichever one is wedged should still be wedged. Whichever one was dashed should still be dashed.
Okay.
Same thing over here. These two should be the same as these two. Question, what if they're both equatorial on a ring? If they're both equatorial on a ring, they can't react. They both need to be axial. Although, if they're both equatorial, they could do a ring flip, which would make them both axial. Okay, so if I had a ring where there was a iodide here, say, and there was a hydrogen, let's put some methyls over here too. So there's only one beta hydrogen. There's not only one beta hydrogen, there's three others. So those three. Let's make this T-butyl, so there's no beta hydrogens up there either. So there's only one beta hydrogen, which is the only one that's drawn here. And here they're both equatorial. You cannot do E2 in this conformation. So they both need to be axial. Luckily, we can do a ring flip in this case. Which would put the iodide down. And now this one's axial. This one's axial. And you could have an alkoxide come in. And now they are lined up just great to do an E2. And in fact, in this particular example, this one would have the iodide almost axial almost all the time because it has this really big group which wants to be equatorial. So that T-butyl group will make this a fast reaction because it'll have those that hydrogen and iodide sort of perfectly lined up almost all the time. So would we lose marks if we forget to draw the ring flip? If we ask you to draw the molecule both forms and draw the elimination off the ring, you need to draw both. And especially if you only drew the left-hand side of this and said no E2 and stopped there, then yes, you would lose points because you didn't draw it in the form that it can react. So you would have missed the whole point that it can react when you have this particular shape. So always be sure to watch out for that. If we asked you the same molecule and we didn't get you to ring flip, like if we didn't ask you to draw the ring, then what this molecule would look like would look like two methyls there. If tomorrow in class is practice 2, yes, it is. We're going to do more practice in class tomorrow. So if you see a molecule like this, you know, that's the same molecule as that up there. But if you recognize that the iodide and the beta hydrogen are trans, and therefore you don't need to draw the rings up top, OCH3 minus, you can do it right here. But sometimes we might ask you to draw the ring out, so you do need to be able to do that. Victoria asks, could you make a list of the types of questions we should be able to do so that we can make sure we practice some for each type of question? Yes-ish. So I'm going to give you my best memory at the moment, and I'm going to give you my disclaimer that I may not remember every possible thing. When are your office hours tomorrow for last minute questions? Tomorrow I'm going to be on between 9:30 and 11. And if you have other questions, just pop me an email. I'll see if I can find Tuesday morning as well, because the midterm isn't until later than that day. I'll send an email, let you know. Possible types of questions. So we have multiple choice. Multiple choice are a number of types. Can you quickly explain what GEM alkenes are? I'm going to do that one first. Quickly explain what GEM alkenes are. GEM alkenes are when you have a disubstituted and both the substituents are on the same carbon. So this would be GEM, this would be trans, this would be cis. Okay, so we have multiple choice. You should be able to, first of all, I would say, identify solvents as being either nonpolar, polar protic, or polar aprotic. Okay. That's something from chapter 6. 2, given starting material and conditions, state mechanism. So when I say state mechanism, just E1, E2, SN1, SN2, that means basically looking at, it's too far up now. We did a lot today. This kind of a thing, right? Like looking at the conditions, looking at the structure of the alkyl halide, or alcohol, then you would use the one that was up above. Pick out the right mechanism. You know, if it's primary alkyl halide, small alkoxide, SN2, sure. That kind of a thing. That's important to be able to do, because if you can't do that, you can't draw the right mechanisms, and everything kind of starts from there. I would say same thing. Given starting materials and conditions, pick major product. Why can't I write on this? In fact, this kind of question comes in, I'd say, like 3 variations. Given starting material and products, pick conditions. So like an example would be if I gave you this, and you know, you had choices of like 1, 2, 3, 4, something like that. You'd have to pick which conditions would give you the product there. Like the answer is 3, by the way. Sulfuric acid does dehydration for alcohols. And I guess the last thing we could do with that is given product and conditions, give starting material. 6, there'd be like stability, like pick most stable alkene out of a group of alkenes. 7, pick most stable carbocation. 8, pick which carbocation can rearrange. Right? So if I gave you 4 carbocations, let's say I gave you pick which one can undergo a rearrangement. The answer is this one. What else do we do? Chapter 6. Oh, maybe like asking which might be faster. So if you have like an SN2 with like which is fastest. So leaving group, of course, iodide is the best leaving group, followed by bromine, followed by chlorine. Which one's fastest? Which one's slowest? If it's fluorine, fluorine doesn't react at all. Fluorine's not a leaving group. Other things. a lot of them, isn't it? The main things you need to be able to do: identify the mechanism and draw them. Oh, there might be questions like, just think of the stuff we did, like rate determining step. If I gave you a mechanism with a couple of steps, which is the rate determining step? It's always formation of the carbocation is always the rate determining step in any mechanism. I might say for acid catalyzed dehydration of an alcohol, what is the first step? First step will be proton transfer. Anytime you have a strong acid, proton transfer is the first step. You should know which solvents are best for SN2s versus SN1s. So SN2s best are polar aprotic, and SN1s polar protic are best. So all the sorts of questions we did today, where I give you sort of a set of conditions and a starting material, and you have to draw it out towards the products, that's definitely something that's going to be emphasized on this test. So the whole written part, almost the whole written part of this test, is really drawing mechanisms. There's a couple of those, and drawing major products based on what the major mechanism will be. Some of them will be straightforward, some of them may involve rearrangements, but you should be on the lookout in every example for rearrangements. You only have rearrangements, though, if it's a carbocation mechanism, E1 or SN1, and only if it's a secondary carbocation that you make. How are folks doing? We're almost at the 2-hour point. I'm happy to go as late as you guys want to go, but we do have class tomorrow, and anybody who's in the other section is welcome to come to that class too if they like. I didn't post the link yet, but the link will be available on Acorn for anyone who's in the other section. Cancel.
I mean, I'm just going to keep doing more of this if we end the call, so I don't mind just keep going.
Okay, want some more examples?
Sure.
What haven't we done much of? This is going to be posted. Yes, it is. Yeah, I am still recording it, I believe. Want me to do another really hard one from an old exam?
Yep, the harder the better. Let's go.
Okay. All right, this was a good one. We usually don't try to trick you up, especially on midterms. Midterms, like once everyone kind of masters this stuff, it gets a little bit easier to do. It's a question like this. No. Wrong conditions. You're welcome. Sam, you heading out? Eat some sleep.
Yep, I'm too tired for this.
Great. No problem.
Bye.
All right. So this was the question that was asked on a former midterm or former final exam. Give this set of conditions, and we said there's no reaction when you do this. Even if you heat it up, nothing happens. However, if you add a catalytic amount of sodium iodide elimination proceeds smoothly to make alkenes. Explain. Okay. Now this one involves a few things maybe you haven't thought about before. What does catalytic amount mean? Catalytic amount just means like you just need a tiny amount. You don't need a lot. You just need a bit. You don't need like a whole mole for each mole of starting material. And somehow adding a little bit of sodium iodide makes this elimination happen very quickly. So the conditions we have here are E2 conditions, and perhaps you can see why this reaction won't go under ordinary conditions is because the hydrogens that are on the beta carbons are cis to the bromine. They're not trans, so if they're cis, that means they can never be anticoplanar. So because they can never be anticoplanar, you can't get E2 because it's on a cyclohexane ring. You have hindered rotation. It can't rotate to get into the right conformation. So the first part you can explain probably based on other questions that are similar to this that we've seen so far today. Sodium iodide part's the tricky part though. Well, what will sodium iodide do? Okay, if you have redraw it out here. You have iodide. Sodium iodide you should think of, of Na plus somewhere up there, and we have iodide down here. Iodide is a strong nucleophile, and we have a secondary alkyl halide. Under those conditions, we expect SN2. There's no reason at all why this can't do an SN2. And if it does, you get this. You get inversion, right, of that stereocenter. The other ones are the same as before. But we still have alkoxide there. And now, after the iodide flipped the stereochemistry, now those beta hydrogens are trans to the leaving group. And now it can very easily do an E2. And it gives you your iodide back, so this can go do that to a different molecule. That's why you only need a small amount. You don't need a whole mole of it because it goes in, flips your stereochemistry, and then gets kicked out. Yeah, so that was a tough one for sure. It makes sense, like, right? When you look at the question at the start, it's like, I have no idea how to handle that. But when you see the explanation, it's like, yeah, that uses completely concepts that we've used so far. The fun stuff really is coming up, though, because the stuff I like is when you can take multiple reactions and sequence them into like an overall. So like an idea is we're doing learning reactions, how to get from A to B. Right? So we're learning sort of one-step reactions. That could be an E1, could be an SN1, could be whatever. We're favoring reactions that give you a single product. What we would like to be able to do is maybe do a sequence of reactions where, you want D, but you start with A, and you can't go from A to D directly, so you got to do it in steps. Now, none of the reactions we've learned so far you can really do in steps, except maybe this one example, because we're doing an SN2 and then we're doing an E2 in 2 steps. So that's kind of like, but when we get to chapter 8, we're going to learn a bunch of reactions that go well with the reactions we already know, and we can start to do these stepwise things. a famous organic chemist named R.B. Woodward. He won the Nobel Prize. He would have won it twice, but he died too soon. He was the first chemist to make a complex natural product from simple molecules, and he made vitamin B12. And he used one of these sequences, and he went A to B, so on, and he eventually got to the product he wanted. It took 60 steps. And 60 steps, if you think about yield, let's say every step was 95% yield, the overall yield would have been 0.95 to the power of 60, which is like really close to zero. So yeah, it was a difficult process, but apparently it took over 200 students and postdocs working on this project to get it to work. But yeah, we're gonna ease into that into the future, these sort of stepwise sequences. We're not quite there yet though, and you're not going to get a question like this on this midterm. So don't feel panicked looking at this particular example and think like, oh my God, I would have never gotten that question, because you won't be asked that question, at least at this point, with what we know so far. We can do just some more random examples just to hopefully reinforce some of the stuff that you've known. Great, glad you found that helpful. This is going to be posted later, so if your brain's filling up, please don't feel like you have to stick around. You can always catch this later. I post everything on YouTube, so on the Acorn site, there's a section which is like exam resources or something, or current midterm resources. I will stick the link there to the YouTube video. Okay, so all right, no problem. See you, Victoria. Have a good sleep. What should we use here? Pick your favorite conditions. Ben, you're checking out too. Victoria's checking out. There should be like a game where, what's that game? What is it? Where you have the box and you have the cards. Black and white box. You know, someone knows that game. Someone tell me the game. Where you have like one card and you gotta like pick a card out of your hand to. I'm really bad at describing this game. Cards Against Humanity. You got it, Ben. Yeah. We should make a game like Cards Against Humanity, where you have one card is your starting material and the second card is your conditions. And you can mix and match any one you want. And then you just get your mechanism at the end. Wouldn't be a very exciting party game, but hey, help you learn organic chemistry. Okay. Pick up a random set of conditions here. Let's go with NaBr. And this is going to do an SN2. What's a good solvent to pick? That'd be a good question. Just give you something like this. Pick a solvent. And we'll go with hexane, DMSO, water, ethanol. So that might be like, I don't know, example of a question. What would be a good solvent here? Hexane would be awful. It's a non-polar solvent. Sodium bromide won't dissolve in it, so it's not going to be a very good one. It'll dissolve in the rest of them. This one is non-polar. This one is polar aprotic. And these two are both polar protic. And the best one to use for an SN2 is polar aprotic. So I would pick DMSO out of this list. If it was an SN1 you were trying to do, then polar protic would be better. Because polar protic stabilizes formation of ions like carbocations, so it makes carbocation formation easier. Anybody else? Anything particular you'd like to see again, or we could do another Sydney, yeah.
Can you explain the difference between the aprotic and protic? Because I always get confused. So
Sure.
like I just need more clarification, please.
Yeah. I think all of the polar protic solvents we use have OHs. So like water, alcohols, OH, carboxylic acids. These are polar protic. Solvents that we don't use that are considered protic also have NHs. So basically, if they can hydrogen bond, they are polar protic. Cameron, yes, I'll get to that in a sec. Polar protic, polar aprotic are ones that are polar but don't have any OHs or NHs. So acetone is one. And it's polar because it has carbonyl group, which is polarized, but there's no OHs. There's CHs, but no OHs. No hydrogen bonding possible with acetone. DMSO looks like acetone, except there's a sulfur in it. DMF is another example. DMF is dimethylformamide. It's polar. They're not NHs, they're N-methyls. And so there's no OH, can't hydrogen bond. And acetonitrile is another common one. My personal favorite solvent. So these are all polar. Typically they'll dissolve, mix with water well. They'll dissolve ions pretty well, or at least decent enough. But they can't hydrogen bond, so they don't really stabilize cations nearly as well as polar protic solvents do. And then we have nonpolar. Yeah, okay, so nonpolar, I think you got, good. So Cameron asks, can we do a question where we're given the product and conditions and have to find the reactant? Sure. Let's do something like this. Now, this is a good one because you can get creative. There's lots of different reactions that could potentially give you this particular product. Now, with sulfuric acid, and we're making an alkene, we know we're going to be doing elimination. Either E1 or E2, it doesn't really matter at this point. You know, what you should do is start thinking about some starting molecules that could undergo elimination to give you an alkene like this. And probably the most straightforward thing to do is, you know, think about this molecule if you put an OH and a hydrogen back on there. Like, kind of think in reverse. You're doing an elimination in reverse. In fact, the definition of the reverse of elimination is called addition. So let's get rid of our double bond, put an OH, put our hydrogen back in there. So that would be an example. Is it the only possible product? Well, it turns out that this molecule that we've drawn has some chiral centers in it. So depending on how there's this, plus it's going to have an enantiomer, which is the mirror image, plus it has a diastereomer. The diastereomer will look like this. and it will also have an enantiomer. So there's 4 possible starting molecules that'll all give this as our major product. Before I leave it, you really want to get creative. How about that? So that, with H2SO4, will give us eventually, in 2 steps, this carbocation, which will rearrange to this carbocation, which will go to that. So, I mean, this is a possible correct answer there as well. So, I actually like giving questions where there's not just a single possible answer, where you can think about it and you can get creative and maybe think about some options, especially if you think about options that I maybe didn't think of. That would be one example. Another one would be like, where there is only one correct answer. I guess there's more than one correct answer, but a smaller set. And I ask you what undergoes this reaction. And I hope you'd recognize this one as being a substitution, that every time we see CN- attacking, it says nucleophile. If it's acting as a nucleophile, it's going to be displacing, it's at a secondary position, so it's going to be an SN2. It's going to be displacing a halide, a halogen. So our starting material should look exactly the same as that, with a halogen where the cyanide is, but if you drew this, you'd be wrong. Anyone tell me why you'd be wrong if you drew that? Tristan.
Inversion.
Good. That's not how we want to draw it. We need to invert it like that. This would be correct. And when I said there's more than one possibility, you could have used Cl or I as leaving groups instead. Those would be fine too. Not F. Okay. Yeah, that's about it. What if I gave you this? No. Something like that. Again, these are E2 conditions, Zaitsev conditions. So we need an alkyl halide where you have X and hydrogen on the 2 ends of where the double bond forms. So something like that, because that can do an E2 to give you the alkene that I wanted. Now, I need more than that though, because every time we ask you these questions, every time we ask you to draw product starting materials, we always say explicitly show the stereochemistry using dashed and wedged bonds. So this isn't good enough. We need dashed and wedged bonds in this particular case. So let's redraw that. I can also draw the rest of the ring. So we can draw I think I drew that on the wrong side. Let's put the hydrogen there. Now, on the other carbon, there's 2 ways around we could have drawn it. We could have drawn it like that, or like that. One of these is correct and one of these is wrong. A is the correct one, B is the incorrect one. Because remember what we're asking of this. We're asking for an E2, and that means that the beta hydrogen and the leaving group have to be anti to each other. That's only possible on a ring when they're trans. So these two have those two groups trans, where this one, they're cis and no reaction. And in fact, there will be a reaction. The reaction will be over here with this hydrogen, which is trans, to give you something like that. Can you go through the steps of how you get the reactant? Like in this particular question. So I guess what you need to do is look at the product first and identify it as either a substitution product or an elimination product. If it's an alkene, it's an elimination product. If it's not an alkene, it's a substitution product. And then look at the conditions and see if that is going to be like a E1 versus E2 or an SM1 versus SN2. So if you have something like if that's your reaction and you have NABR in water, then you might look at this and say, well, we've got a tertiary alkyl halide. This is going to be a substitution, so it's going to be SN something. And then your choices are SN1 or SN2. Realizing that this is tertiary, it's not going to do an SN1. So, sorry, it's not going to do an SN2. So this is going to be an SN1 reaction. So you think about it, what could react to do an SN1 and give you that product? And it could just be as simple as removing the bromine and putting something different there. Like that. So we're doing a substitution. We're substituting the iodide for the bromine. That's not the only possibility. You could have Cl instead. Keep in mind that's not a chiral center, so we don't have to worry about RNS. How about something like this, though? Well, that one could too, right? Because this is SN1. Actually, that's not going to work because this is probably going to do an SN2, which would give you yeah, scratch that idea. But sometimes drawing things out that you're not sure if they're right or not and realizing after that they're wrong, like I just did, is a useful part of the process in coming up with the right answer. Like play around with it, try some different things. It's not like there should be one answer only and it's in your head and you're good. You can play around with these, you can try some different things, and you can get answers too, which may not be the best answer, but they're not bad answers, right? So like if what would be a good example? If I gave you a question like this. Keep going to these cyclohexanes. Let's get rid of cyclohexane for now. A longer chain. No, this is a bad example. Okay, I want something like this. Here we go. So here we have a reaction and you want conditions. There could be two sets of conditions that could do this. You could look at this as an SN1. And if you looked at it as an SN1, then the conditions that you might consider using would be water and no heat. So this would be just sort of like room temp or cold or something like that. And if you did something like this, what could happen is the molecule would do an SN1, lose bromine, make a secondary carbocation, water then attacks, wrong stereochemistry. Like that. And another water molecule comes in to remove the hydrogen, and there you go. So you might say, this is the reaction I want to propose. Okay, and that's how I'm going to get that product. And this is a correct reaction. This will give you that product. But the problem is, at this particular step right here, it could also give you this, which would give you so it does give you the product you want, but it also gives you 50% of a different product. So I would predict that would be 50% yield. This would be 50% yield, and you'd end up with a racemic mixture. So this reaction is fine to get you there. It's just not the best choice. A better choice would be something like NaOH, which is more likely to do an SN2, which would give you inversion, and there you go. Now, you might notice NaOH is an example that we avoid using. You probably maybe have not seen any examples with NaOH up to this point. And the reason is hydroxide is both a strong nucleophile and a good base. So if you go back to our chart way back here, you know, we have small alkoxide as one unit, strong nucleophiles and other, like hydroxide, like treads that line right there. So for secondary, you get like a mix of E2 and SN2, so it's a bit messy. So we kind of avoid it because it's more clear cut if you use an alkoxide as the base or you use any other nucleophile but hydroxide. So I kind of regret bringing up that example, but there you have it. You go over the difference between a nucleophile and a base. Yes. So a base, when we say base, we mean Bronsted base. Umlaut over the O. So a Bronsted base is something that accepts protons. And I know Lewis base got a different definition and whatever. We don't mean that. We mean accepts protons. And bases can be strong bases or weak bases. And weak bases are not very good at accepting protons. Weak bases could be something like fluoride. You know, they're not very good bases. Strong bases are basically hydroxide And for the reasons I just stated, we avoid using hydroxide. So instead of using hydroxide, we use alkoxides. So if you think about it like this, we have hydroxide, we have alkoxides that are small, we have alkoxides that are bulky. These are, hydroxide is an excellent base. Excellent nucleophile. Small alkoxides are excellent base. Maybe moderate. These are excellent base. Terrible nucleophile. So if you're doing an E2 and SN2 competes, go for the bulky base, with the caveat that that'll give you Hoffman elimination if possible. Small alkoxides, they're much better bases than they are nucleophiles, so they favor E2. Hydroxides are kind of good at everything, so that's why we kind of avoid them, because they almost always give you some E2 and some SN2. Nucleophiles, so basically this is sort of it as it comes to strong bases. There's lots of other ones, and we will see other ones when we go forward, but if you're trying with alkyl halides to do E2, this is all we're going to be using in this course. A whole bunch of other ones that are possible, like NaNH2, sodium amide is a very strong base that we'll be using in upcoming chapters. Alkynes, if you deprotonate them, they make molecules that are both very strong bases and very strong nucleophiles. There's a few things I've kind of avoided in these last two chapters, using sort of borderline things like hydroxide, like this. We're simplifying everything to be these two types of strong bases that are in that table. Everything else, if it has a negative charge, we're going to consider it a strong nucleophile. So I think the examples are N3-, which has a Lewis structure. Looks like this. It's called azide. We have cyanide. All these are bases, but they're all weak bases, so they're not good for E2. None of these. This is just hydrogen sulfide is what it's called. We'll just call it, generally it's sulfides, where H can be R. Halides, Cl-, Br-, I-, F-. These can all be nucleophiles. Fluoride typically only if you have a polar aprotic solvent, not polar protic. Any other nucleophiles that we looked at? I feel like there's some I'm forgetting about. Again, there's some, generally speaking, if it's negatively charged, it's a strong nucleophile. If it's not negatively charged, I think we also looked at ones like this. So like sodium salts or potassium salts of carboxylic acids, carboxylates. Good nucleophile. Negatively charged and not an alkoxide. Yeah, so the difference is between a nucleophile and a base. Bases love to go for protons, nucleophiles love to go for carbons. So if we gave it an example like The nucleophile goes there. The base goes there. How's everyone doing? Jennifer, you probably have more energy than any of us. You're in a better time zone. All right, should we call her a night? Great, we've got 2.5 hours done. I will post this recording so everyone can see this on YouTube at their leisure. And thanks all for coming tonight. If you have any questions, drop me an email, send me a message in Teams, anything like that, and we're good to go. Tristan.
Yeah, not much of another question for tonight, but do you mind if I just kind of drop into the office hours just to hear anyone else's questions, even if I don't have any myself?
Yep, absolutely.
Okay, sounds good. I'll probably be there.
Great, perfect. See you then.